Welcome to my presentation on control and communication co-design for network systems. My name is Karl Johansson and I'm at KTH in Sweden. I would like to thank the organizers of the 6G Wireless Foundation Forum to allow me to speak here today. And particularly since I'm a control engineer, I'm delighted to talk in front of many people working on the new generation of communication systems. So my area of expertise is in network control system, and I've been working there for some 20 years or so. But what I'm going to talk about with you here today is some very recent work of the last year or so involving these couple of PhD students and two former postdocs. So what in general we are interested in when we say a network control system is a systems where physical processes are controlled over a wireless network. So wireless communication makes sure that sensors and actuator information is being sent securely over this network. And of course, from a communication network viewpoint, I don't have to argue why this is important, because with 5G and coming 6G, we will be able to control more and more processes, closing the loop over such networks. So we need to understand this. There is also a strong pull from the control application viewpoint. In industrial automation, there is still a lot of control loops which are closed over wired networks, and by making them wireless, we have great possibilities to actually save cost and increase the possibilities that we can do improve these processes. So let's make it a little bit concrete what we mean by these processes here. So I took an example. I took a pulp and paper mill, Iggesund, located a couple of hours north of Stockholm. You see in this picture the pulp mill and the paper machine, which is used to produce, in this case, this premium cardboard. In such process, there are many different sub-processes going on. One is the so-called starch cooker process, which I draw the block diagram for here, where you see that there is a handful of actuators and sensors, which is controlling this chemical process in a good way. In total, in the plant here, we have thousands of control loops, maybe 5,000 sensors. They are today all closed, these control loops, over wired networks. But in the future, there might be great possibility if we could actually monitor and operate such a plant completely over a 5G or 6G network. So today, if you just look at the starch cooker process here, it's a very centralized system. So we have the process, but basically all information is being communicated up to a central control station where all the commands and so on are being computed. In the future, it's not only so that we need to move all the way to that this is fully wireless, such a process, but it's also very interesting to just consider the case where you in an easy way could add perhaps some sensors, like in this case, in order to improve the process. So today it's very difficult to do that. There is no flexibility in the system, but if we could do that, hook up sensor nodes here, it could be very convenient, and that could give great possibilities. So let's look into something we have been doing, a PhD student of mine. So you see a little bit from a control viewpoint, kind of the limitation you have today on doing like handover and working more with ad hoc communication systems. So in this case here, I have a couple of inverted pendulum, a couple of processes that requires quite high bandwidth in order to be controlled here. They are located at A and B in this picture. And then I have a control node, which is located at 18 there. So in this particular experiment, the student demonstrated here that this process over here, that these can actually be controlled by a wireless node that we can move inside this overall wireless network. So the wireless network here is able to actually carry the information and to close the loop, the sensor communication to the controller and the controller sending back to the actuators despite that we are now moving this over this wireless multi-hop network. Of course, with a 5G setting, this would be something that was very easy to do. But I wanted just to indicate here that there are small things that could be also a great advantage if we could do that in many of these processes. Let's now come to the core of this talk, come to the co-design of the communication and control. And I want to indicate with some math here a particular problem that we recently have worked on. So again, it's a network control system here. We have a plant that we are controlling with a controller that communicates now over this cloud. So what is the formulation of this? So we have a plant given by a linear time discrete system driven by some noise here. So a very typical model for a control system. The network here, we need to have some abstract model of the network. In this particular case we look at the very simple network model. We say that we have a capability to regulate the resources of this network in such a way so that if the network, if we put more resources in, then the message will be delivered in a shorter time to the controller of the plant. While if we are putting less resources in, it will take longer time. And there is a delay controller that is basically regulating this. So you see here, it's a very simple model, but it's a quite natural model also to imagine now that we could put a price depending on what link, in this case, you choose to communicate over. So with such a model, now we can ask ourselves, so could we formulate a reasonable problem where we are able to make decision in a systematic way, both at the plant controller and the delay controller? So the first thing we have to notice here is that the information structure for this problem is a non-classical one. So the information at the delay controller is the one I give here, but that is different than the information structure of the state of the system at the plant controller. Notice that the state of the system here includes both the state of the plant and the state of the network. For such a problem now, it's natural to think about that we would like now to optimize something which involves both the control performance as well as the cost that of using the network. So this is a cost function here, which then depends on the actual control cost that control action we take, as well as the decision we make about the network. So such a problem, which might seems to be a straightforward one, is actually quite hard to solve. And this type of problem where we have so-called a non-classical information structure was studied in the 60s and 70s. For instance, Witzenhausen and MIT did some seminal work in this domain. Of course, not motivated by network control system, but for other type of problems. So here for this network control system we wonder now that if we have this optimal control and network delay control problem, what can we say about the solution now? Does the solution have some interesting structure that we can utilize for deriving the optimal controller, as well as coming up with information about how it should be implemented? So the first thing we can say about this setup here is that it actually is supported by the separation principle. So this result now, as you see here, tells us that the optimal plant controller has a classical structure, as you see. So U here is given by a linear feedback, where the feedback is given by the standard Riccati equation, so back to Kalman in the 60s and so on, right? So this is interesting, right? Because now we see that actually the optimal control does not explicitly, the structure of the optimal control does not explicitly depend on the delay controller. It depends on the optimal estimate of the plant state, but not explicitly about the delay controller, which is a nice feature, right? So what about the estimator now? What can we say about that? So the estimator, we can also explicitly tell what that should be, and that's given here. So the estimator would have expression you see here. And notice now that in this expression, we do depend on theta. So we do depend here on the controller of the network. So what else can we say? Yeah, so what about now the actual optimal delay controller? So the delay controller here would not have a nice structure for this formulation. So the delay controller, we can formulate now the optimal delay controller as a mixed integer nonlinear program, as you see here. In practice now, we can solve this by using standard relaxation techniques. And that gives us now approximate solutions to the original problem. So let's now illustrate the solution to this problem for a couple of examples. So in this case, we regulate the second order system. I have a network which now have 5 different links. I have the fast link, so to say, cost me 20, while the slow link, 5 delay link, cost me 1. When we solve this problem, you see here to the right, the optimal link utilization that we get. So it's quite interesting to see that most of the time, the optimal thing is to use the slow link, to use the link with delay. But now and then, and more or less periodically, we jump over and use the fast link. So this is interesting from a viewpoint of what is the optimal thing now to allocate the network resources versus the control performance that we have. And this now generalizes perfectly also to a larger system. Of course, this would not be reasonable to do just for a single loop control program. But let's say that we have a larger system here, we can do that as well. And before that, let me just indicate for the single loop system that, I mean, with this approach, I can now draw the optimal trade-off of the communication control. So I can visualize and actually see now where I would like to be at this curve. But let's go to the larger system. So what I describe here perfectly extends now to a large multi-loop control system. In this case, we have capital N number of control loops, but you see that it looks very much the same. We have a centralized network manager, which is now allocating the resources to the individual network links that we have. So we could visualize that also in a layer structure where you see that in this case, we would have the application layer and the plant. In the application layer, we'll have the plant control and delay controller, while the network manager would, of course, reside in the network layer. So if we look at such a situation now with 20 control loops, 20 plants, again, different network services, that depends now on the delay that we allow in the different links. So very similar to the single loop case, now we can consider this multi-loop setting, and we can now plot the link utilization that we use. We take for all these 20 loops, which of the different link resources will be used. And you see that it's a bit similar, but of course it looks more complicated than in the single loop case. But you see that we have here a tendency of using certain links more often than other links. But this is now done, so to say, automatically with the algorithm that I show. And this seems to be a reasonable thing to do now if we are looking into the situations where we have this type of dedicated channels in a cellular network. So with that, let me come to the conclusions. So what I would like to really stress here is that with 5G, 6G, new wireless networking technology, we have a great possibility to close much more control loops over these networks. It's very few today which are actually used like that, but we see, and we are working on many different layers. I showed here also something we are doing with the platoon control using very similar type of techniques. It's important to be able to guarantee the stability, robustness, and safety that are required for this control application. So there needs to be a systematic way of doing this co-design. And in the cases we have limited resources, it's important to take them into account the performance that is needed for a specific control loop. I would also like to stress that it's important to understand the application and doing experimental demonstrations and evaluations of this approach. And we do it in different domains, as you see here. There is, of course, many more things that I would be happy to speak about here. Something we are looking into now is this mix about data and model-based approaches, because as we grow in the number of control loops that we can connect here, it's actually not so straightforward to just use model-based techniques, since these models might not be available. So how do we mix now learning approaches with that? Other work that we do is related now to making security guarantees or privacy guarantees for these closed loop systems. So with that, I would like to thank you very much for the attention, and I'm more than happy to take any questions if there are any. Okay, thank you so much.